Don't pass the command line. Like what the you don't running and just like 3 days. Think that
So then to select the box to change all materials.
So we need more screen?
No, I think we're good. This screen is good. This one is weird. I don't know why. You can ignore it.
Yeah, does it drop?
No, I think it's a different scale. I think it's just a long.
Screen two is great.
Yeah, screen two is great.
Yeah.
I don't know how to make it show up correctly over
Is it
here.
like a focus?
No, it's not focused so much as zoomed.
Just picking up the wrong
Right.
resolution.
Right. It should send all.
So
Yeah.
we're using
HDMI. I got this. I don't. Yeah. I don't know. Left from my perspective or from their perspective. Yeah. Nothing changed when I did that. I tried left before, so try it right. And now this one. Okay, so that one. I think it's just what it is. I mean,
so was the right one.
yeah.
I'm gonna try switching
Well,
and then switching it back.
okay, so that's this computer. Yeah, that one looks good. This one is this computer here, which doesn't do us any good.
No, switching back didn't do anything.
Yep.
You take your screen to, what's your resolution set on your screen?
I like 4K. It's a crazy nice
If you
monitor.
go to 1080p,
Yeah,
it'll probably show up correctly up there.
I lost my mouse.
Yeah, the projectors are supposed to be on the scale, but sometimes they're.
Maybe if you had both of them show. That's an idea.
So I've got extend. Yeah.
That's even worse, isn't it?
Ooh. Yeah, I don't know. It's weird.
You're not even running Mac. It's usually the people running Macs that really.
Yeah. I think we'll just accept it the way it is. I don't know. It's what it is. Well, shall we get started? Bill's run off. I don't know where he's going. So. All right. Well, welcome back to Alarm. It's the first one in what, almost 3 years, 2.5. So glad everybody could make it. So if you're not familiar, sorry, this is this monitor, I guess, right? It's the one that is actually got all the screen on it. I don't know why. If you're not familiar, LabVIEW is Advanced LabVIEW Architect for the Rocky Mountains. Thanks to Buddy for arranging this room for us. Thanks to Original Code Consulting for the food. It's great. And I'm recording this, so if you need a copy for recertification or whatever, let me know. So, we'd like to have more of these. At least I think we'd like to have more of these. So I got a couple questions. If anybody wants to think about it, chime in on the forums or talk about it now or afterwards. But I put up meetings on the website for January and May. Who wants to organize them? There's a volunteer. So, and where? It's great that this is here, but do we want to keep having him here? It's a long drive for some of us. So if we can find a place. Yeah, that's great. We used to have them up in Boulder area, but the NI facility went away. If anybody's got any ideas or places we could have them.
Long time ago, we used to do it. Well, I was.
Yeah.
I could try
Yeah.
to get room. I don't want to do it.
Yeah.
I can give you some ideas.
Yeah.
I can give you some ideas.
And then similarly, question, it's great that OCC and Dave have given us some food, but I don't think that makes sense every time. So, so if there's a way, it's great. It's great from my perspective, but I don't know. So,
I'm sure that was one time.
yeah. Do we want to just brown bag it in the future, or you know?
What you might consider is
Okay.
they lost their NI connection. And I was like, when they went to their local distributor.
Okay.
And said, hey, we get a bunch of Latin people who buy hardware.
Okay. Yeah. Yeah.
Well, in the US, I've been super. Europe,
Yeah.
Yeah, it's good to bear.
Well, it's all ideas worth pursuing. So, yeah. So agenda, I've got a presentation from Dave and Davida about speech recognition and output in LabVIEW. Bill VanArsdale, is that right? Pronunciation? Fitting data using random search. And I'm going to talk about building a hybrid CREO and PLC system with DQMH. So, yeah. So I think I'm going to hand it over to Bill and this picture is Colorado National Monument out near Fruita. So, yeah. All right. Thanks, Bill.
Well, nice to be back. Glad to see you guys. So I can get this going. All right, so this is fitting data with a random search. It's an old idea, but it was new to me. It's dedicated to the memory of Jonathan Olson, who passed in November of 2019, unexpectedly. Jonathan had come to some of these meetings. He was I'd consider him an exceptional LabVIEW programmer. Anyway, so let's look at motivation for this. I'm not sure how this is, it's not showing up at all. What am I doing wrong? So I had it on a slideshow. But apparently that's not enough, right? So what am I looking for?
Get on my screen. That little blob right there.
That's the one I did.
Yeah, that one.
Yeah, so I did that, but it doesn't show on the screen.
Drag it to that screen.
Is it that one?
No,
No,
it's, let me do this.
go ahead. Let you draw it. It's big. That's maybe your.
Yeah.
Okay, I can size that down.
Do the,
Is this the Galaxy Quest? One moment, please.
yeah.
Ooh. Yeah, so I just yeah.
All right, well, now you can't see it here.
You can sit over here, I guess. I don't know. Whatever it says.
I was doing that earlier.
Yeah. Yeah, this one's always a different resolution than that one. So I don't know what its problem is.
Well, maybe if I make them both. You mind if it's a little smaller on that one?
Great.
Since you're all sitting on this side of the room. Oh, I need this. Right away. Where is that? Sorry. Is that all right? It's okay. All right, so I gotta do this. Anyway, that's Jonathan. So let's look at the motivation for this. I had a two constant model and I wanted to fit some nominal stress data as a function of stretch for some vulcanized natural rubber. Okay, and I wanted to fit it in 3 experiments simultaneously. So the experiments were equibiaxial, where you're pulling in 2 directions at once. You get this in a spherical balloon, for example, right? That's or sclera like your eye. And then there's uniaxial, where you're just pulling in one direction. In planar, you're pulling in one direction, but you're constraining it in the other direction to not change length. So anyway, that's the data. And I was able to fit these 3 curves simultaneously to 2 constants. And I did it by just searching randomly for the constants. So basically, these measurements are each complicated functions of what's called the stretch, which is the ratio of the current length to the initial length. So you can see rubber, you know, over 4.5 times its initial length, right? Which is no surprise if you've ever stretched a rubber band. So you know, you would typically have to go to some other program to do this, and I didn't want to do that. And I was just playing around with coefficients, you know, just tweak it this way, tweak it that way. And I realized, you know, maybe I could automate this in LabVIEW and just let it tweak it until it got better. So you need some measure, something called a merit function that indicates whether you're closer, right, to the good fit. This top plot, by the way, is what are called residuals. This is the difference between the data and the fitted value. So for example, like see this guy here, that's up here. And it's normalized by something called the root mean squared error, which is essentially the standard deviation of data about the fit. So typically standard deviation is about the mean. So the fit in some sense behaves as the mean. And we'll go into that in a second because you're going to want to know. So LabVIEW has a good VI called goodness of fit that does this stuff for you. Okay, so you feed it, say, n data values here, and then you feed it n fitted values corresponding to some m parameter fit, 2 parameter, whatever it is, right? And I didn't use the weights. So if you had information about the uncertainty of data, you could use the weights to weight some points over other points because they were considered better data. But I didn't use that. It defaults to 1. You can just ignore that input. N minus n, in other words, number of values minus the number of parameters is called the degrees of freedom. So you have to have that for this VI. So out of it, you get a LabVIEW error code if you want it. You get the sum of squared errors, R squared, which is called the goodness of fit, root mean squared error. It delivers those 3 things. Okay, so let's look at those quickly. So root mean squared error is essentially a standard deviation where this piece, the data value minus the fitted value squared summed up over all the data points is the sum of squared error. Okay, so in a least squares analysis, what you end up doing is minimizing the sum of squared error. Okay. Well, if I minimize this, I'm minimizing the root mean squared error. Okay. Now the goodness of fit is 1 minus a ratio that involves the sum of squared errors divided by a difference between the data value and the mean data value. So it normalizes it. So if the sum of squared error goes to 0, then the goodness of fit, the R squared goes to what? 1, right? Yeah. So, and you've probably seen this in plots, right? You've seen R squared values. It may be a slightly different R squared, but this is one LabVIEW spits out that's useful. To my mind, it's better to try to get something close to 1 rather than something close to 0, because 1 is there and 0, you're like going way out. Maybe, I don't know, but they're equivalent. So you know, least squares, I just thought it was nicer to maximize something rather than minimize something. So we're essentially looking for m parameters to fit n measurements. And I'm going to look for the value R squared closest to 1. And it's equivalent to minimizing SSE. And questions on this? So you got this VI in your pocket, and you can use it as a merit function for this kind of search. So another function that VI that I'd mentioned that is useful is this remove outliers in essentially the same place. And what it does is it allows you to window data. So You can window it in the X direction or in the Y direction or both. As well as there are other, range types you can apply. So this is how you would use it. If you had a plot coming in, which is in a cluster of Y and X arrays, you're basically feeding it this, you're specifying some range type and you're specifying the range. And that's it. It just takes them out. It's very fast because it uses the LVNal, DLL, that a lot of these analysis routines use, the mathematics toolkit. So, all right, this is my LabVIEW pseudocode. So maybe it's bothersome to you. I don't know. This is the algorithm. All right, so I've got X, Y data. Here's Y, here's X. I need to feed, and this is for one data set, just to keep it simple. But I need to feed Y in so I can compute R squared. And then I need to come up with the fitted values. Okay? So you have an initial guess of coefficients. And you're going to bring this in on a shift register, and then you're going to create new coefficients randomly that are close to your initial set of coefficients. And you're going to march around this way on the surface where you're trying to find this maximum R squared. So you have a surface that's basically R squared plotted as a function of however many fit parameters you have. So this could be a 3-dimensional plot for 2 parameters, or it could be a 4-dimensional plot or a 5-dimensional plot, depending on how many parameters you have. And you're looking for a maximum in this surface. And then, so I need a VI that's going to calculate these coefficients that are close to the ones you started with, sort of randomly perturbed from that. And I'll show you that VI in a second. The other VI you need is the one that calculates your function given the X values. So I have these X values. I'm going to feed that to this function. I'm going to calculate f of X. These are essentially your fitted values. You would have to write this VI anyway, right? If you were going to fit some function. So if you were to use one of the fit routines that's sort of not one of the line or the polynomial or standard functions. There you go. Yeah, you would have to write this function. So you need this. And then I'm going to use this goodness of fit VI. I'm going to calculate R squared, and I'm going to go, is it better? That's it. Is it better? If it's better, well, great. I'll keep it. I'll put it in a shift register. I'll bring it around to the other side. The initial guess for this is something, like -1, something it'll never hit. So fine. If it's not better, I'm going to use the old one and just move that one back. Okay. So in other words, I'll just stay with that. And it's the same thing for the coefficients. If it's not better, I'm going to use the old coefficients. Otherwise, I'm going to use the new ones. And I just put in a shift register. That's it. This stuff's really pretty fast. It's just function evaluations. No derivatives, no gradients, no. You're just evaluating your function. So how do you stop? Well, you stop based on a count. So I initialize a count 0. If I get something better, I reinitialize the count to 0. Okay? But if it's not better, I increment. And then I check, well, have I hit a limit? So you're going to specify a limit. I'm going to try 100 times to get something better. And if I don't get something better, I quit. That's it. So you can control, how much you're willing to keep tapping around with the white cane until you find something better. That's it. Questions on this? Okay. This is a really, really sensitive wheel. So this is how you change the coefficients. Okay, so I have an array of coefficients. I'm going to check to see whether they're not equal to 0. Because one way to disable a coefficient is just to set it equal to 0. And if it's 0, I want to keep that. So that's this here. So if it's not equal to 0, I'm going to change it. Otherwise, I'm just going to set it back to 0. I don't care. Okay? So I have these coefficients, and I'm passing the value in here. I'm going to multiply that value by some delta, 0.01. So I'm taking 1% of the coefficient value, right? 1%. And then I'm going to multiply that by a random number that's between plus or minus 0.5. That's it. Okay. So I get essentially a perturbation on this coefficient plus or minus 0.5% of its value, the way this is set up. So the way I have the VI set up, and you can download the VIs, I put them out. I control this. So you can set that to depending on the kind of resolution you want in your coefficients. So I add it to the old value and I'm done. Very fast. Boom. So each coefficient is perturbed with a different random number, right? Because I'm picking off a new one every time in this for loop. Okay? But it's bounded between plus minus and 0.5. I did it. Measurement. So maybe it's to make it slightly clearer. So I have a model that looks, say, like this. I just made this up. There's nothing real here. But it's two coefficients, C1 and C2. I've got a square root and a log. I just threw stuff together. Okay, and then I have a measurement that's a prediction of this model. Okay, so, and I made this up too. So essentially what you're doing here is you feed in little x values, that gives you a big X in here generates your y value. In other words, that's the prediction of that model in that measurement. Okay? So you have your function, whatever it is, but it could break down like this. The key is this is some known function, some known prediction of the model in terms of whatever the model spits out. And then this is the part, the model that you're like trying to show up to fit whatever reality is across however many measurements you have. Okay. Yeah, this is here. Let's zoom in. So in this first part, I got data, right? I'm just saving data as plots. So this is XY, cluster of XY values. What I'm doing here is I'm collecting all the Y values from these three plots and concatenating them up as this. So those are all my Y data values, okay? And then I'm spitting in all the X values, the X arrays, because I need those for each different measurement. And I have 1, 2, 3 measurements. Okay? They're just functions, whatever they are. And I'm going to concatenate those up to give me my fitted values. Okay? And I'm going to compare the Y values, which I concatenate only once, to this. Yeah, I know. Maybe I shouldn't concatenate like that in a loop. I actually think the compiler is smart enough to optimize this now that, you know, it's like way simpler to present it this way. You could clearly go other directions since these are all a fixed, you know the size of this array up front. So you could initialize an array and then just replace, right? Which would be cleaner, but I'm not even sure it matters anymore. This is the little BI that does the coefficients. So the coefficients get fed to each one of these guys. And that's it. And then, so is it better? That's this check. No change. Wow, I'm using the original coefficients. I put it back in the shift register. I increment this count. At some point, if the count exceeds the limit, I'm done. Okay, that's it. That's all there is to this. So let's look what happens afterwards. Well, I get to pull R squared and root mean squared error out of this because I have those from the last time we checked here. Okay, so that's some of the stats I have. I also have this percent of root mean squared error divided by the range. This is sometimes called the percent full scale. So full scale is whatever your total range is on the y-axis. And root mean squared error is a standard deviation. So it actually has units of whatever the y is. So if you really want to look at something that is non-dimensional, you have to divide it by something like the range. And it turns out it's a useful stat to have. I got the number of attempts. But what I want to focus here is I get the coefficients out. I was saving the coefficients as a cluster. So at some point I converted the cluster to an array. It's easier to manipulate. I'll show you on the front panel in a sec. These VIs right here, essentially what they do is your fitted value, the curve, will only have as many points as you had data points. That doesn't always give you a smooth curve. Okay? So what happens here is I up the number of points. I redo in other words, I'm just upping the number of X values. So I already know what the function looks like because I already know the coefficients. So now I get a smooth fitted curve instead of one that looks like it's segmented. Does that make sense? Yeah, this is a standard trick for getting, if you're doing a line, right, it doesn't make any difference. But if you're doing a polynomial and you don't have enough points, your curve is what? It looks like it's one straight line segment to another straight line segment to another. So you get a smooth curve this way. This is something that's well worth doing. That gets me these three plots. I concatenate them with the data. I put it out as a graph. Okay. So, okay, here's the result. So I started with 3 different functions. That's my model. These are the predictions in these 3 hypothetical experiments. I got 18 points in each one. I started with a model that had coefficients 2 and 4 and Gaussian noise. And that's how I got my data. So I have data that's sort of normally distributed about the fit. But it's one way to create data, right? You start with something you know, and then you can play with up in the noise. So the data is the model plus noise, okay? Now I've got these black squares, red squares, blue squares. I go to fit, and the routine gives me numbers that are close to 2 and 4, as you might expect, okay? I used a limit of 100. In other words, I was willing to try 100 times with no improvement before I gave up. I set the delta to, 10 times smaller than what I showed you in the VI. Okay, instead of 0.01 is 0.001. Under 1,000 attempts, boom. That was it. Pretty good R squared. 998. You know, and I've got scatter about these fits. See how the fitted curves are smooth though? Otherwise they would be straight line segments. Essentially, I get a value every time I had a fit. So as long as we're clear on that. That's the root mean squared error. It's, you know, the range here is like 0 to 7 roughly. So dividing this by 7, I get about 1.3%. So just as a ballpark, I consider an excellent fit 3 nines. And, you know, full scale percent less than 1%. So I'm not quite there in this fit. Questionable fits to me are like 2 nines, less than 2 nines, or, you know, greater than 2% full scale. So if that's the case, either you have noisy data, which is possible, or you have a bad model. And you can usually tell that, right? In this case, it doesn't look like the model's bad because the data looks like it's normally distributed about the fit. See that? That, you know, and if you were to look at residuals, which is the difference between the data value and the fitted value, you'd essentially see stuff above and below whatever the 0 was corresponded to the fit. Questions? Yeah. How much time to do this?
For the total calculations there.
This is like blink of the eye stuff. So in other words, I've got these coefficients on sliders, and you can basically, because all routines basically have some initial guess for the coefficients, right? So say you're way off, it's not going to find it, right? Won't find it. And it really doesn't matter what routine you have. You can find a little niche somewhere where I don't care what kind of least squares thing, you know. In other words, you're not guaranteed your surface is sufficiently concave down that it'll just find its way to the top. But you can play with the things and it'll start snapping it, like in real time. Like and then it's there. No, it's just function evaluations. It's extremely quick. You know, and this, you know, what, 1,000 on a computer you have is going to be, yikes. It's all very fast. And it doesn't require anything. No derivatives, no gradients, nothing. Just your function. And the only things you really have to play with are these two. You know, what kind of limit do you want, and what kind of precision do you want in your coefficient? Because if that number is really coarse, it could stop at a place that's close enough and give up. Right? But if you tighten it, it'll go, no, now you can do better. Eek. So anyway, this VI is there. You can play with it. See how. What? Yeah, it comes up pretty close. What you're asking is how flat is your surface that you're looking for the maximum of, and you can, you know, this surface turns out gets flatter, I think, the more coefficients you have. because coefficients will start trading off amongst themselves. And so you can find something nearby that's about the same, right? Yeah, I'll show you an example. But it's pretty repeatable. That's one, you know, and you can play with it, you can perturb it, you can see if it comes back, you can, because it's essentially interactive with these controls. So this is an example of an individual fit. This is viscosity data for polymer solutions. What I want to point out is the range on the axes is enormous. Okay, this axis goes from 0.05 to 1,000 and 0.001 to 10,000. This is huge range of data. Okay, the problem with huge range of data is the large data values up here will dominate the values down here. In other words, it just ignore the data because the small data is close enough. It's the large data that drives everything. And so what you have to do is you have to normalize the data to get it back into a range where things are sort of equally weighted. So the easiest way to do that is to take a log base 10. So now my axes go from minus 0.13 to 3 and minus 3 to 4. In other words, now I'm in a tight range. You know, and I think the point is, if you get much outside of 10 or 50, I mean, you're really starting to where you can have large data values completely dominate small data values. Okay, sure, if you're 50 to 75, it doesn't matter. But if you're 75 to 0, it does matter. So it's best to normalize if you can. Just briefly, this is a 4-coefficient model. One of the coefficients is the limiting viscosity at high shear rates. You can see where the blue curve is trying to do that, but the red curve and the black curve, no. They don't show a limiting yet. And those limiting values at high shear rates are hard to get because they're at very high shear rates. There's the equipment that can do that kind of stuff is like unusual. I mean, water is typically said to have a constant viscosity, but if you were to shear it at a high enough rate, it would probably shear thin like this. So it would look kind of like the red curve, and then it would decrease and then hit a limiting shear rate, when essentially all the water molecules were essentially aligned in some way. It's insane. It's insane. It's insane shear rates. One way to look at this is the relaxation time in these liquids. So polymer molecules have this huge, you know, very long relaxation time. Water molecules have, you know, relaxation times that could be nanoseconds, maybe tens of nanoseconds. So the inverse of that is the shear rate, roughly where it starts to bend. And 1 over a nanosecond is what, 10⁹? Nobody has equipment to really do this. So anyway, this was fit using the same algorithm. It's just a single plot. So these are different materials. So this isn't 3 separate measurements. It's just a single measurement using the same fit algorithm. What if you have really crappy data? Okay, so what do you do with this? Well, one thing you can do is you can just fit a straight line through. Yeah, I mean, this is a type of data where they see this as climate temperature anomaly data and climate stuff. It's all over the place. And it's it's hard to, I've blown up the axis here. But what it's really low values of R squared, 0.08, 26% full scale, full scale. So, I mean, it's not what I'd call a great fit. And this fit was obtained using the coefficients literally from the NIVI, LabVIEW VI, that just gives me slope and intercept for a straight line. So, but if you look at the data, it looks like it trends up, maybe flattens out, maybe trends down, maybe flattens out or trends up. It's hard to say. So if you were interested in finding that kind of information out of the data, what you could do is something called a segmented fit, where you fit straight line segments that are connected, and you're looking for something called the breakpoints. And the breakpoints are the boundaries of the intervals where the segments exist. And those points are useful because you might be able to say, oh, well, this happened between this year and this year, for example. And then something else happened later. So this data was actually created using that kind of segmented straight line type thing. So I've got an intercept of 5, and I got breakpoints at 2, 5, and 8. In other words, here, here, and here. I've got 4 intervals. And I had a slope of 0.1 in the first interval, 0 in the second interval, minus 0.1 in the third, and 0.1 in the fourth. And I added a ton of noise. 0.2 that's 0.2 standard deviation Gaussian noise. You can play with more noise, but this was scary enough for me. So I'm going to use the same algorithm. So this is the data, and it looks kind of like 0 slope. Okay? Kind of. If I were to fit I didn't do it, but if I were to fit a curve through here, it might, maybe it's down, maybe it's, I don't know, pretty flat. This is it blown up, and then I've colored the intervals. Okay? So you can see them. And so this was auto-scaled. So using the algorithm, all I'm searching for are these breakpoints. The rest of the stuff is determined by the linear fit VI. So that gives me the slopes. It gives me intercepts in all the intervals. I shift the intercepts so that I get a curve that's continuous, right? Bing, 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 bing. I got close in this case, right? Here's close to 2, close to 5, close to 8. Slopes, not, 1.11, close to 0, minus 0.12, 2.3. So you can compare them to these values up here. And you see, okay. But there's more information here than with just a straight line fit. So this is really crappy data, right? It's very noisy. And the problem here is, and that's what it would look like, again, colored. And with the VI, I included, you can turn the colors on and off. So you can sort of guess. But that's this stuff, just not auto-scale. You can see the R squared's better than maybe a straight line fit would be, but still bad, So that it's not going to snap to this. This is not you can throw the crappiest data in the world and say run, and you're just going to get great numbers because your surface is not really have a good peak in it. it's got a lot of flat. And in fact, there are places where it can get stuck because, oh, well, that's about the best I can do here. But I could do better over here. I just can't get there because there's a little bubble there that it gets stuck in. So, so this is somewhat interactive. You have to end up tweaking the breakpoints a little bit. So if you go home and try this and you say, well, it didn't work. You have to interactively fool with the breakpoints. And you go, slide it, you know, and it's really quick. It's like, that's better, and it snaps to the thing. But it can get thrown off. And that's because the data is like so horrendous. All right, so a couple observations. Sure.
So I've got really messy data sets that they analyze signals. What I've done in the past is I've done like a moving average through it. And then I did this is just neat, simple, stupid. I did a polynomial fit to the moving average.
Yeah.
Just
Yeah. So that's like smoothing.
yeah, exactly.
Yeah, and smoothing is so I'm not smoothing. I'm essentially fitting. So in other words, I'm just fitting with a different kind of function. So when you smooth, like you could fit it with a spline, right? That would be a smooth or a polynomial or, yeah. I mean, all the satellite measurements are all calibrated with a polynomial up to fifth order polynomial. I mean, that's it. They just, you know, if I input this, you know, what temperature do I get out? And they fit the, no, and it's not a, so in that sense, you don't have a model. I don't have a model. I'm just looking for a segmented curve that might pick out trends. So we're at the point here where I don't have a model for this. I don't know what to do. I'm just trying to trend it. And if you know, up to this day, it was like this, but then it was like this, and I don't know why, and then what happened, and maybe there's information there, maybe there's not. Yeah. But you're right. You don't have a great model. And the other examples I showed you, I had real models that fit either multiple measurements or a single measurement. But I happen, you know, I know that in one case, the model's good because I generated the data using the model. In the other case, it's just a frickin' great viscosity model. The best. So, all right, so quick observations. This is not limited to any, you know, it doesn't matter how complicated you are. If you can write a VI, you have it. It's no complicated algorithm in the background. You control the algorithm. You can simultaneously fit using the way I suggested, sensitive to initial guess, but this is every fit. Doesn't matter how you do it. Does not involve derivatives. And one of the deals about derivatives makes curves more singular. Okay. Integrals smooth curves, derivatives go the other way. So every time you have to take a derivative, you are at risk. Equivalent to least squares, you got to normalize data if it's over a large range of values. I would avoid models with more than 4 coefficients. I mean, if you got a good reason, great. But at some point, you know, maybe that's not really the answer. And then you have to what? You have to just smooth or do whatever you do. So, and then you can also use it to trend noisy data by looking for breakpoints. So I'll leave it at that. Am I good? Did screw up? Go too long? Way long?
Just kidding. I have a question.
Yeah.
So it's like, and goes to the basis of your algorithm. Take, for example, your original data with a 2-parameter model
Yeah,
and endpoints.
yeah,
And imagine you're going to let it do 100 random guesses around your initial guess. Why is that better than doing a raster over a 10 by 10 evenly spaced grid of those parameters centered at your initial guess?
so it's not just 100 attempts.
No, I know.
No, okay.
Your limit was 100, you actually did 1,000. I'm just saying, as an example, say.
It took it a while to zero in, and then finally it zeroed in, and then it couldn't get any better, and it's.
Right, but what is the benefit of doing this random walk rather than in your 2-parameter space rastering over that same area with evenly spaced guesses? And when you find the best one, then you can zoom in on that and raster over that.
No, you could do that. You could, yeah, I mean, this was brute force.
Okay,
Yeah, I mean, that might be a great way actually to figure out, hey, where to start.
but why is it not better to figure out where to enter? What is the advantage of doing random? And the one advantage I can see is you don't have to write your rastering calculation. You don't have to set up your loops to do the raster.
No, yeah. I mean,
Back in the 1970s, when computers were a little bit slower than we are today, the Monte Carlo approach was essential to
Right.
here was recommended if you had a large number of parameters, because then it's like, okay, well, just find some random spots and we might hit something. Whereas if you went and tried to do the entire raster, yeah, with 2 parameters, like, yeah, you probably can do it, but.
yeah, too big an array for those days, yeah.
Got too many parameters on
Yeah.
there. Your computer, will get the answer next year. And so, it's the Monte Carlo approach is, to get data faster with a large number of parameters.
Yeah, I guess my answer would be, it seemed like the least amount of baggage. Basically, just tweak it, tweak it. Yeah, another question?
Well, I just had a similar question to Dave, and I was thinking, like, if you did the whole raster, instead of stopping at the first one, like maybe multiple ones are better, but I think you really said problem.
Yeah, it really comes down to, do you have any hope your model is any good? If your model is, in some sense, not good, this isn't going to make a silk purse out of a sow's ear, right? I mean, you're really talking about properties of the surface, and is this surface reasonably well behaved, or are there lots of pits where it can get stuck? That all depends on your model. And I don't know. I've had good luck with this. And I'm not saying it will fit bad models. And I'm not saying it'll fit noisy data. Like if you have really noisy data, how are you going to tell whether your model actually is great? You're relying in some sense on your data being clean. And if you're convinced your data is good, then you don't have anywhere to turn except, my model sucks. If you can't describe it. And the other thing is, I don't know the range on some of these parameters. Basically, on the coefficients, I'm not sure. In fact, in some cases, I was actually surprised that a coefficient flipped negative. And it turned out there was actually physics attached to the flip. And I go, ooh. So I wouldn't have guessed that it would go negative. So I don't know what to say on that. Other questions? Okay. All right. Let's see. You gave me my stick back, right?
Yeah.
Yeah.
I wouldn't mind, but if you don't want to have to switch the computer out.
It's easy. If we want to record yours, or if you want, are you logged into Zoom? No? Okay. You still have HDMI or do you have?
I think so.
Okay. Very display. Let me grab my mouse. Let me just trade seats. Yeah, I don't know. It's probably this crappy little thing here.
So this is going to be real sort of sweet. I just mentioned to somebody that we've done speech generation and speech recognition in my Microsoft program, which you haven't but anyway, Microsoft is a LabVIEW program that we use in a lot of presentations, right? Modular, all that stuff. So we thought we would do speech recognition, speech generation. And I got to give credit to my intern, Vita Bird. She worked with me for a little over a year ago. And went to school here in Lines last year. Worked with me again last summer. And she did this probably about a year ago, probably. So these routines for modules. So what we're going to do is the goal was to create a module in Micah that lets make audible notifications. Alarm goes off or something there across the room, not their computer screen. And the other end of it is, could you make speech recognition so that you're not by the keyboard, you can just issue a command and just experiment to go off and do something. So that's what we wanted to do. The process I used to accomplish that goal was get the intern to do it. So turned out that made it really easy for me. She, I believe, found this example on ni.com. This stuff is not terribly hard. The example helps a lot. So get that. I tried to find Microsoft's API documentation. I found this link, and it's not even clear to me if this is the right document. So good luck. Need to dig into this further. Maybe that's a good place to start. I don't know. Anyway, so the results. It's actually really easy, at least to do what we wanted to do. It works. That's great. Caveat is, I didn't do this. I don't really know the details of the API. If you want to ask questions, you can ask maybe. I'm not going to guarantee that she knows it either, because it was a year ago. So anyway, that's why she's here, in case you guys have questions that she may or may not remember the answers to. So, quick demo. Here's our program Micah, and right now I created a little configuration file that sets us up to simulate a reactor. Of course, it's a reactor. So start it up here. Got my license key. So now we get the 30-second delay as punishment for not having a license copy of Micah section. So insert interesting comments here. There it is. We're not licensed. So temperature specifies. And what will happen in just a couple more seconds is it will exceed its safe limit.
Reactor temp is over its limit. Current temperature is 4,009.
Demonstration worked. Very impressive. So what that looks like in Micus is this is just a sort of a test panel in Micus. I don't have to have it show up here, but this is the module here. Right inside Micus, and just
Be sure to get pizza.
make it say whatever you want. The way the code was, here's the module inside Micus. So here's the .NET reference. We're opening it in this case. This is really simple. Those strong things. When you hit that button that says send, it takes the message. This little VI replaces any channel name with their value. That's why I got to tell you the temperature. And then you hit this .NET node, and it does all the Microsoft magic. Right? You get text, you get speech out. So that's really all there is to it. So since I'm not going to give you all the codes of Micus, just to give this one example, I did.
So what version of .NET?
It's probably 4 something. It's whatever, whatever tends to load with LabVIEW these days.
Okay.
Anyway, so this is speech generation in Micus boiled down to a single VI. Boy, that's really tough. Not to criticize Davey's efforts, but there's not a lot there. Now, if you go to the example that on the NI forums, it looks a bit more like this. And one thing I did is I disconnected an error wire from here to here because something weird is happening on my computer when it gets here. This loop is like, find all the voices that are loaded on your computer. So, you can load different voices with different tonality and whatever. And so this is good code. If you want to use a different voice, you can scrape this code and figure out how to do it. But there is a little weirdness with this loop. It finds 2 of the 3 voices on my computer and then errors out. Anyway, ignoring that, I just took that wire out so it wouldn't stop. Here's you notice the default voice of my computer is David. So that's but
Can you get it to say, I'm sorry, David, I can't do that?
spoil all my good ones. Hey, so here's
LabVIEW is the greatest software ever to be created. Next to this fork, there is no better invention.
and you might have noticed I was manually clicking the stop button on the last time I was talking. So that was 0, by the way. So if you like that voice, use 0 instead. But the point there is this thing really hangs up the UI. So you might want to keep your speech segments nice and short. It's right on your program. So that's speech generation. That is super easy. So the next question is, how can we do speech recognition? So going back to our program here, we have another module that we configured to run it here for speech recognition. We can make it run in off, so it's not listening to us. Test.
Speech recognition set to testing. Commands will not be executed.
Yeah. So you can talk to it now, and it won't actually do the command. You can tell it's or you can turn it off.
Speech recognition on. Commands will be executed.
Thank you. All right. So now, let's see. Turn reactor back down a little bit. So now we're running again. The reactor starts to get hot. Oops. Mike is add coolant.
Command issued, add coolant.
So that's how that works. And in the background, it ran a sequence that lowers the temperature of the reactor. Unfortunately, we're running late to exponentially, so that didn't have a huge effect. But in the speech recognition here, you see we've got one phrase that it's organized to recognize, and then it responds. It recognizes.
Command issued, add coolant.
I did not say that. We'll get back to that part in a minute. So how does this part look?
I have a question, Dave.
Yes.
Do you have to train that to recognize?
Command
the voice?
issued, add coolant.
Right, whoever is
Because
saying.
obviously that's
please stop saying that.
Or training.
No, when Dave started first working on this, I thought we thought we were gonna have to, and I don't know, she did some magic and made it the I called it in. Basically, I didn't have to train anything, and it works on this one. So that really has to do with Microsoft's speech API. So do you train the speech API? You probably can make it work better.
Oh, so you train outside of the lab?
It's totally outside of lab.
Okay.
So I won't give a 100% answer on that, but my recollection is when I put this on a computer, it just worked.
See, I remember turning speech to text on or whatever on Windows, and I remember asking me to do some training.
Yeah, we got that too, and we thought we were gonna have to do that. And then there's a much higher threshold, we're gonna give this to the customer. That didn't turn out to be good. Anyway, this is what the code looks like. Again, in the init case, we've got the .NET reference opening, and then it goes down to here. This is where the interesting stuff happens. I'm not going to explain all this right now, but there's a bunch of stuff there. And then when you say something and it's recognized, this is where the response is. This isn't really where the work is done, but this is where the response is. So we've got an event for a value change event for the speech recognition. Command recognize control, which is this string up here. And when this event fires, then all it does is it speaks back and acknowledges that the command was recognized, and then this little coded, this sequence here is actually issuing a command within minus that it recognizes. So the question is, how does this event fire and what the heck is going on? So let me turn to that. It is, and that is so weird. That's not planned. So I boiled that down to an example here. Class dismissed. I recognize it. So the score is 0.94. And if it's above, this threshold, then the green light goes off. So it's recognizing a bunch of stuff that's below the threshold right now. So this is the guts of what you saw in Micah's, just cleaned up a little bit into a single VI, see what's going on. So in this case, we're feeding it a bunch of phrases that it's going to learn to recognize. So we're only doing that case where you're trying to match known phrases. We're not doing a case where you're trying to create a string with an arbitrary bunch of words in it that you're dictating. So that's a different thing. You have to investigate if that's your use case. So we tell the .NET framework that we've got those phrases. We call in and get all kinds of references to other pieces of the .NET framework that I don't understand very well. And eventually, we register a callback with this VI. And as parameters, we send it the reference to both that score and that string. And that callback PI is kind of the heart of it. This is where after the .NET does its work, it pushes information back onto this PI. This PI then gives out the text that it recognizes at the store, and that those references are then used to push it up to the top level PI. So my question for you is, how many people use callbacks in LabVIEW? That's one more that I maybe
I
expect.
didn't watch when I taught the class.
I just started today.
Okay.
Yeah.
It's been a while.
I knew it was
Yeah.
possible.
I'm sort of vaguely familiar with the concept, but I've never actually had a reason to do a callback directly in LabVIEW. Anyway, that's black magic in LabVIEW, and again, they learned LabVIEW as part of her internship like a year and a half ago, and then started doing this callback.
So for those who don't know, basically a callback is like an event without an event structure. Basically,
Basically,
like
that's
whenever
what
that
it is.
event happens, that VI gets executed. More or less, black magic under the hood.
Yeah.
Black
Okay.
magic.
Yeah, cool.
No, it's not that crazy, I'm sure, but it's just not something I use a lot. Anyway, that's how it works. And the last piece I was going to quick demo.
So I have a question, Gabe.
Yes.
Has this just been a side project or is this something you're actually shipping to customers?
Open the pod bay door, Al.
I'm sorry, Dave. I'm afraid I can't do that.
All right. So
It's the obvious joke.
one of the lessons I've learned years ago for being a consultant doing LabVIEW, never add anything that's not needed to your program. Right? You're wasting your time. Well, this is one reason I love working with my assistants. I just add anything I think of. And sooner or later, a customer needs it. No, nobody's using this. So, and that's part of the caveat, actually. Yes, my last slide. So, yeah, this speech recognition, we can't do arbitrary text dictation. I don't know, that would be interesting to figure out. I'm sure the Microsoft API could do that if you dug into it. Another thing is, you heard how we echo the command back. So the idea is you're in the lab and you say the command across the room, you want to know that it happened or not, right? So it echoes it back. If you do that, it's possible to get it into an audio because it hears itself say the command and then issues it again. So in the spirit of Alexa or Google, hey Google, we've added a prefix. So we say Micus and then the command, and then the command's echoed back without the prefix, which means most of the time it doesn't catch itself. And we also have the option to turn off that echo. So those are the two fixes we have for that particular problem. But there's other caveats like noisy environments that could be definitely problematic, and it's just not all that robust. It's not like when you're sitting there working with a mouse on that computer, right? So you might not want to use this for mission critical functions. Yeah.
So military, you can't have it. Now, we looked at this at one point and couldn't have a microphone on the ops room. Flying us out. Fine.
Someday they'll make it.
Well, no, you wonder, with better headsets and stuff like that, whether, because, if you saw Blade Runner, you want this, right? It's just the case, zoom in, back, no.
So anyway, any other, peppered Davey with really difficult questions about how the API works.
One use case I could see for this though would be like some sort of like accessibility thing, right? Somebody who like has trouble typing or whatever, pressing buttons, like. I could see that being somewhat useful in a very specific setting.
Gordon Kirchner, hooked up his audio quick drop.
Yeah, yeah.
He did that where you could do your quick drop commands
Oh, wow.
spoken.
Yeah, how many years ago was that?
That was a while ago. That was
That
like
was-
2009 or something.
Yeah.
That's pretty old.
10 years ago.
Yeah,
Wow.
so he definitely had it, all of this way back then. It's cool.
And yeah, the bulk of it is just built into Windows. You don't have to load anything up special.
Yeah, I don't know if Norm was doing his, he was probably doing the same thing. Yeah, I never actually.
It should be better now.
But he wasn't using that.
He might have been called, I don't know, he might have been called the all, there might be.
Yeah.
I don't remember, but.
Sure.
They're cramming more and more stuff. We don't want to deal with it.
I can't, this screen turned off. So. What is it doing? All right, well, I guess it's what it is in terms of this. All right. So I think that's the only screen that's going to have everything on it, so. Sorry. Talk about what I've been doing at work for the last while. I work for a company that makes Coriolis mass flow meters. They're super expensive industrial equipment, basically. We have a large test lab where we test these prototype flow meters, see if they're working correctly, temperature control, vibrating, what all kinds of stuff with them. We have a lot of systems that use LabVIEW, about 30, and we also have a bunch of systems that use a programming system called LabVIEW. And a lot of these machines require some sort of external cooling. So chilled water, heat exchangers, all kinds of stuff. So and this is time consuming and it takes a lot of energy, stuff like that. So we've been building out a lab-wide chiller. So this is a picture of the actual chiller. It's 140 tons of chilling capacity, which is a lot. It's pretty big, as you can see, it's outside. And we're going to distribute that chilled water all over the building. So right now we use external chillers, just a big standalone thing that requires 480 volts and chills water with a little onboard pump. We also, as the system heats up, just dump that water down the drain. It's super good for the environment. And fill it back up with cold city water. And we have a few machines that we just are directly connected straight to city water, flow straight through and straight down the drain. Once again, fantastically cheap and good for the environment. So a couple of problems. The external chiller heat's rejected into the building. So this chiller is inside the building. cooling this machine and dumping this heat out into the building, which our HVAC now needs to extract from the building. HVAC systems aren't really designed for that. They're really designed to cool off people, keep people comfortable. So they're noisy, big noisy machine sitting next to you all the time. Takes up a lot of floor space. And many of these are too small. We have a couple machines there where the chiller is just too small, can't keep up with the load we're putting into it. So total loss cooling. Warm water is dumped down the drain and city water is temperature down. So a lot of water wasted. It's expensive. The city keeps, the county or whoever keeps charging us more money for our water. We also use this water as part of the testing procedure in these flow meters. And we need that water to be at a stable impurity, basically. That water has to stay at a specific purity. And it's pretty hard to control that temperature precisely. Within a couple degrees is all we can achieve. So these direct connection things that we use, once again, it's wastewater. It's not great. So this lab-wide chiller, what's it look like? A little P&ID here. So the large chiller is outside. We have a flow meter on board to turn that chiller on. We just point at the screen to make it easier. Where'd my mouse go? See it over there. So there's the large chiller. There's a mag meter on board to monitor total flow through the system. We'll talk about what this is a bypass. There's a pump in the system to actually flow the water, and then you can have multiple calibration stands connected in parallel to this system. So multiple pieces of equipment, each would have an onboard flow meter, onboard control valve, and an onboard heat exchanger. So talk about how that works. Any questions about this sort of the basic layout of this system? So there's a bunch of components in here, obviously. There's piping all over the building. There's a chiller, there's a mag meter we just talked about, there's the pump. There's some safety around that pump. Is that pump exceeding its pressure rating? Is it actually got water or glycol in it? Bypass, that bypass has a control valve and a mag meter. There's a main control panel, a big industrial control panel, which we'll look at in a minute. And there's a bunch of other safety and monitoring stuff in there. And then there's each of these individual machines that gets connected to it. And I think when we're fully built out, we'll have, I think, around 15 of these. So machines connected to it. So kind of a weird picture, kind of looking up, but all this black piping along the ceiling here is this lab-wide chiller or system for distributing it. So this is where it goes outside to the chiller itself. This piping that's coming down is to that pump. This piping leads off to one end of the building. This piping leads off in this direction, and it's behind this crane, unfortunately, but there's more piping that leads off to the other end of the building as well. So if you need a good piping contractor, put big pipes in up at your ceiling. These guys did a fantastic job. They did a really nice job of it. So, main chiller, we just looked at it. It's a York YVFA 140-ton chiller. So it's actually 2 chillers on board there that it stages them in as necessary. So here's this flow meter. It's a mag type flow meter. It's basically a magnetohydrodynamics. You flow liquid through this moving magnetic field, and it senses the flow. So, and that has its own individual little control box that's talking to it. The heart of this is this flow meter. Well, we'll talk about it in a second, but that little box in the control box, the little one with the display, is monitoring that flow meter and controlling the chiller itself. So, picture of the pump. It's a 40 horsepower pump, bunch of stages, centrifugal pump. There's a couple pressure transmitters on the upstream and downstream side. And then the funny little thing in the middle is a level switch. So it has basically a fork that's vibrating a little, and if there's fluid between the tines of that fork, it says there's fluid there and it allows you to run the pump. If there's no fluid, the system is drained or whatever, it won't let you turn on that pump. So just keep that pump safe. So there's this bypass. We'll talk about what it does in a moment. But it's up near the ceiling. It has a control valve and a flow meter in it. So, and once again, there's a little control box to talk to it. So why do we need this bypass? Well, if you look at this sheet here, it says minimum flow rate in gallons per minute for that chiller is 250 gallons a minute. The max is 580. So if you are running less than that or less than the minimum or the max, well, if it's more than the max, the chiller just can't actually chill the fluid. But if it's less than the minimum, you're in danger of freezing that fluid. So basically that control box, this one here is monitoring that flow rate from this mag meter. And it says if it's between these numbers here, turn on the chiller. If it's outside of those numbers, turn it back off. Just keep everything safe. So that's why we have a bypass. So the answer is, so the reason we do it is, let's say you have a machine hooked to that and it only needs 100 gallons a minute of flow. Well, you'll never get the chiller to turn on if you only are 100 gallons a minute. So this bypass will open up and get you the other 150 gallons a minute of flow to get you to that minimum number. So you can always have the chiller on if something needs chilled water. Main control cabinet. Well, basically it would be consuming flow that you might want to put somewhere else because you have a maximum of 580 that bypass is just open all the time. You would be consuming some of that flow. So any machine, some machines might only need 10 gallons a minute or something. So you need to dynamically control this whole system. So a main control panel on board is the main CREO system here. There's a VFD that's controlling that pump. Bunch of other safety circuits, the usual sort of stuff, same control panels, power supplies. So, and then each machine that gets connected will get one of these boxes that has the hybrid part of this. I thought about putting NI stuff in there. It's expensive. So I have these little PLCs. We'll talk about why I chose these PLCs. But we get 3 different systems connected, 3 different styles of system connected. So each of these has these little PLCs. So there's 3 styles of connecting these systems. There's the heat exchanger is in the flow path. So this picture's a bit unobvious, but no, go back. There's this large 275 horsepower circulation compressor. It's moving gas at up to 700 PSI, comes out of this side, goes through this red heat exchanger, goes out through this machine, and then comes back in this way. So this heat exchanger is in line with the flow. And you can see there's a large glycol line coming down. It goes, it's hard to see, but it comes in the heat exchanger and then comes back out and goes back out to the chiller. So we have to dynamically change this flow rate through the glycol side of this heat exchanger to maintain the temperature in the system. So that's one of the ways that we are controlling temperature. The second system where the liquid that's being chilled is not in the flow path. So in this case, oil at up to 80,000 pounds a minute is coming through this pipe, but we pull some of it out, run it through we pull it out with this pump here, run it through this heat exchanger, and then out through this flow meter and back into the system. So that's a second way of controlling it. So the glycol side of this is kept at a constant flow rate. And then we just vary this pump speed to get to the desired temperature. So it's a second way of controlling it, that this system has to accommodate all these different methods. And the third method, there's really nothing to see. It's just a pipe connected to the top of this thing that glycol comes through and goes back out the other side, back into the system. So it's this flow through type machine. So I think the important point is a little bit of complexity in this system. So how do you build this in a way that works well? So a couple of design requirements. It's got to be easy to add systems because we're not building this all instantaneously. We've got to be able to modularly add these one at a time. I don't want to spread wires all over the building. I'll lose my mind threading analog wires throughout the building. So it's got to be inexpensive. It's got to be, cost effective. So self-managing, headless. I don't want to have somebody got to go click around and do this or that to tell it to turn on. And there's a bunch of PID loops throughout the whole system. So there's 2 in the main system, 1 to control the bypass, 1 to control the main pump for total flow. And then each system we add has yet another PID loop to control to the desired flow rate. So you can do a lot of PID loops in LabVIEW, but it's a bit painful to build them up. So, my other requirement that I added was only Ethernet between these components. I don't want to run many extra cables. Just want to have a little system-wide network. So what meets my requirements? How can I make it easy to add systems? I did a bunch of work about this. What actually is easy? So C-Rail, it's great. It's great stuff, but they're $3,000 a pop. And it's a bit expensive to be adding to these because that's nearly the cost of everything else we have to add. So I don't know if you ever use these Acromag modules. Pretty nice. Lots of IO on one little simple module. Price is pretty good, a couple $100 a piece. Network communications, I can talk to them over the network, but there's no onboard PID and there's no way to program them. So it's a choice. It wasn't my first choice. I could have done the PID on the C-Rail. Company I work for, Emerson, makes these RTSI things. They're a bit pricey. Same problems though as the Acromag. There's no onboard PID. So what I finally found, which I've used before, is these Click PLCs. They're sold by Automation Direct. They're cheap. Has all the IO I need, has an onboard PID, especially only the Ethernet modules won't have this. Network communications, everything I need right there in one box. This box is on the order of $150. Super cheap. The question is it reliable? And I've got some of these Click PLCs I've had running for 10 years straight with no problems in an incredibly harsh environment. People welding, they're literally connecting to welding machines. So super electrically harsh environment, dirty, people grinding stuff near them. They just keep working. So if you need a cheap PLC, I can't recommend it enough. That's what I went with. Software side, I could have done a lot of things. It's a very modular system. All these little pieces only have the most basic interaction with each other. So what can I do? I could do actor framework, but I don't really know any actor framework. And every time I look at it, I'm like, this is a lot of work for something kind of straightforward. EQMH, Sam taught a nice class in it. I've been using it more and more. I like it. It's good stuff. So there's a thing called decaf. It's out there. You can download it. It's not really supported. It's kind of weird. I don't know. So I went with DQMH. So let's talk about, yeah.
I was just wondering if anybody else could mention up there that it's unsupported. Does it seem like, and I kind of keep up?
Yeah, it seems like another thing they've given up on. Yeah.
And I get, so it was like a side project, I think, that was semi-supported.
Yeah.
And they're moving along the highway. And then when NXG came out, they were gonna implement all the features of NXG, so it stopped working with that.
Yeah.
And then NXG fell down and nobody wants for that.
Yeah.
Get back up. It is open source, so.
Okay.
If you want to maintain it on your own, you're welcome to do that. You
Okay.
can do that, but,
Yeah. Okay.
That's kind of the deal with that.
Yeah, it's weird. Yeah. So this is an important point about all this. All these little things are pretty standalone. All these pumps and valves and bypasses, they don't really care what the other parts of the system are doing. They just have to do their thing. So the only thing that's passed around is the system itself overall healthy? Is it in error? Is it in fault? Can we, and if required, the bypass, for example, needs to know what flow rate to be set itself to. So that's the only thing that has to go around. So it's pretty nice for a messaging stored point. It's a pretty minimal number of messages that move around. So systems are super easily added in DQMH. You say, just spin up another clonable module. I've got 6 systems, spin up 6 modules and talk to each of those modules independently. And the only thing you need is an IP address and if a name, which is just user friendly, so the person can figure out what the heck they're looking at. I don't know if you've ever used anti-doc, but it's a fun way to, an interesting way to document your system. So here's a little bit of a drawing of what, the different parts of my system look like, these different modules inside of my program. So I don't really have a lot to say about anti-doc, but try it out if you're using DQMH. Nice way to document stuff. So let's talk about all these modules. I got a bunch of them. Emergency stop. There's emergency stop on the system. It's pretty easy. You read the emergency stop, and this is a key thing I've done to minimize the amount of data moving around. I don't know if you're familiar with this LabVIEW VI. This has the data change from the last time it came in module or block here. So if emergency stop is changed, then go ahead and tell people that emergency stop is changed state. And if it's now on, the things that are subscribed to it will safe themselves. So pretty easy to understand. Everything else just shuts down. If you push emergency stop, it goes away. Shop air, this system requires pressurized air to function. So I have a pressure switch. There's a very crappy picture of it. It's as simple as you can imagine. It's feeding into a DI in the control system. If I don't got shop air in the building, system shuts off. So I have a stack light so people can look around and say, is it functioning? What's going on? They're just discrete outs. Once again, they're just subscribing to that status. Red means the system's in fault, green means it's good, yellow. So these individual machines can be in fault and the system itself will keep running because I might shut down that machine for maintenance. The rest of the system doesn't care. And then blue just tells you the chiller's on. So just so you can glance across the room and see what's going on. I use this RT monitoring stuff to see if my network or my system is running well. Just another DQMH module in the system. Keep this watchdog running. Reboots the Serial if it freezes. I have no idea. Is there a way to test this? I have no idea. Yeah, right. I could force it to stop doing it. I've never noticed it freeze. Yeah, I have no idea, but it's there. It seems like good practice to put it in there, but there it is. Another DQMH module. I have an onboard UPS to allow my Serial to ride through power bumps. I monitor that. Once again, if I go off, if power drops in the building, my Serial keeps running, distributes out to the rest of the system. Hey, shut down now. So
Yeah, I just say, you could probably test your watchdog by just killing the LabVIEW process. But SSH is kill the LabVIEw process.
yeah, I don't know. I never tried it. Yeah, I don't know. We'll try it, I guess. Yep. So there's an onboard battery. Keep track of that battery. If that UPS goes into fault, I save the system as well. So the chiller, I want to monitor that chiller. So there's, I could talk directly to that chiller with Modbus, but I'd have to add a serial card to that. So I just use the Click PLC that's in the bypass, and it has Modbus built in. And I just ran a cable from that Click over to my chiller. And it's a bit hard to see, but my LabVIEW code just calls these parameters inside the PLC. They're all on Modbus TCP, so you can see
DF302 is DF302 right here. So I'm writing DF302 here, and I'm reading it back out over the image module to get that piece of data.
What is the cable between the click and the chiller?
Just a network. Oh, between the click and the chiller is a 2-wire Modbus cable, 485, Modbus 485.
So the click is just passing the bus connections on through.
Yep. Well, no, it's not passing through there. I've programmed it to do these commands. Read the current state of the chiller. Is it healthy? What's its output temperature? That sort of stuff.
So you program the click to talk Modbus chiller.
Yep.
But why not just talk Modbus chiller?
Because I'd have to add a serial card to it and then run a long cable across the building.
Well, you had to run the Ethernet cable.
I had to run the Ethernet cable to the bypass no matter what, but this would be an additional cable, an additional module. So it just simplified that to me.
The click's talking to something like this. That's the real time.
It just simplified how many cables I had and how long those cables had to be. So, yeah. Same thing with the magmeter. Same click is talking to this box in the magmeter box, reading data about the state of the magmeter. Is it healthy? What's it currently measuring for flow? So,
And how do you program it?
it's this ladder logic here. So if that's actually one of the nice things about the click is that their programming language is free. So you just tell it, read these Modbus addresses and put that information into a particular variable. And then you can read any variable from the click over Modbus TCP. Go ahead. It's pretty easy. This 485 stuff is pretty easy. It's pretty much drag and drop. If you want to do something with the more basic serial commands, like talking to a Mettler Toledo scale or something, you've got to do some finagling around to get that timing right, where you write and then you wait and then you read and all that stuff. But it's not bad. Or maybe I'm just a crazy person who likes teaching himself more programming languages. So once again, another module just spins it up on startup, says, here's your mag meter. Bypass, that is running on that same click PLC, and I'm monitoring its status here. And you just set up a PLC saying, or set up a PID. Here's your inputs, here's your outputs, here's your scaling factors. And off it goes, running to a target that you ask for. So, and I just monitor it over the network. So, pump. So this is how you set flows. You write into that to get, and that once again has an onboard PID. I say, I want you to target this flow rate. Here's your current flow rate. And it starts driving itself up and down. If you say I want zero flow, it ramps itself down and then disables itself. So it's off. So it's not consuming any energy. And in the module, and we'll get to that in a second, is I'm also monitoring temperature and pressure. If those goes out of spec, the system saves itself. There's a little rude comment here. NI Modbus is crap. Interestingly, this particular VFD, the way you talk to the VFD itself rather than other parts of it, other than the control module or something like that, is you have to give it a specific address, even though it's over TCP. And Modbus, NI's Modbus driver won't let you do that. So don't use that on Modbus. So here's the code that's keeping track of the VFD. So this is my personal Modbus drivers that are substantially less crappy than NI's. There's this analog input, reading these analog modules and reading this level switch. And so it both reads it and spits it out over the network. Does that make sense? I don't have an example of the code in the pump because it's just parameters you write to it. So each system gets this PLC, and part of it is defining an API programming interface to this. So this PLC monitors the status of the system and itself, And if everything's good, it sends out a healthy signal to the control system of the machine that's attached to it. So that machine doesn't have to know anything other than the chiller is available. That's all it knows. It doesn't know anything at all about the chiller. It's available. And then it just closes a discrete into the PLC saying, I need flow. It's programmed into this PLC how much flow that machine needs for most examples. But the example, the first type of system I talked about, where it needs to vary that flow, it's an analog in, and you say, how much flow do you need? And it comes up and down as necessary. So that API is very simple from the perspective of the machine that it's attached to. Clonable DQMH module, I spin up as many as I need. So any questions about how that's sort of the big chunk of DQMH that's sold with DQMH. So it's getting this clonable thing to work in a very programmatic way. Onboard PLC, or not PLC, PID loop to drive that flow to what you asked for. It's that very simple read if that discrete input is closed. If it is, fire that command, or you're reading how much flow it's requesting. So if that DI is closed, it tells it whatever number you've programmed in the PLC. If it's open, it says 0, and that just comes back into the system. Here's the ladder logic for that. It's not real obvious what's going on if you don't know ladder logic, but basically it's reading the parameters, checking the safety of the system, starting and stopping it as necessary. There is a safety monitor, so if the system is in fault, the PLC is in fault, if you stop communicating with the PLC, it safes the system. So much of that. And then there's this top level that does all this. So it concatenates all these statuses. It adds all the requested flow rates and then distributes that to the pump and the bypass. And it only broadcasts those if there's a change. So if the status is still good, it just doesn't tell you. It just keeps doing nothing. If the flow rate hasn't changed, it keeps doing nothing. It doesn't broadcast stuff to minimize work in the CREO, to minimize network traffic. So here's a screenshot of the main. You can see each of these DQMH modules starting on the lost track. Anyway, so on the left, that's where I start all the DQMH modules on startup, and then it's pulling in these statuses here. So as the status changes, it fires a DQMH event, says write it to the overall event, the overall status. And then on startup, it also goes and turns on each of those DQMH modules. So it's monitoring what I asked for. And the stuff at the bottom here is reading a list of this machines that have been attached. So reads an IP address out, writes it out. So it starts the individual modules. That makes sense? Pretty complex system. Overall status monitoring, it's just reading all these status. It concatenates all the statuses. It reads them all. If anything is in a fault where the system should shut down, it fires this set status to fault mode and goes off running. And that is distributed out to the rest of the system. The other nice thing as I've done is it's self-healing. So if, let's say the VFD goes offline, the pump goes offline, comes back online for whatever reason, it just comes back up and running. You don't have to go push any buttons. It's all headless. So you don't have to think about it too much. Flow rate is pretty dull. Concatenates it adds all the flow rates you've asked for and spits them out if it's changed to the modules. So that need them, which is just the bypass and the pump. There is a user interface. It's just mostly for calibrating stuff or adding and removing stands. But you can monitor everything through it. You can look at everything. Why is it in fault? You can go dig around in it. Get this nice overview screen, just a repeat of the lights, how much chilling capacity you're using, the temperatures, how much flow you've asked for, how much flow you're getting throughout the whole system. So this is the same PNID. You can look at things a little more closely, see what's happening where. Probably the important part of this is the mouse is here, is you can pick which one of these stands you want to monitor. So and it just dynamically, if you've got 10 stands, you can just pick 10 of them. So whichever one you want. Adding and removing a stand is pretty easy. So you can monitor the status of each stand, but if you want to add a stand, just go in there and type in a name that makes sense to you and the IP address of the Click PLC and hit add, and it's in the system. It's automatically connected. You can calibrate the analog ins on the pumps if you're really, those pressure gauges on the pump, if you're really desperate to get 1/10 of a PSI accuracy on something that. So, what can be improved? I wish GQMates made helper loops for you. Sick of making helper loops. And this is all, the system's pretty new. Is there some race condition going on? Too many things trying to write to things, because with the DQMH modules, the timeout, when you fire a command in DQMH and that timeout, that resets the timeout. So is it firing too often? So I never get to that timeout. So it's not doing the monitoring that I want to do. I don't know. I'll find out. Yeah. Okay. Okay. Well, it seems like an obvious thing. So. Yeah. Sorry, I don't have any code to show you that's live because, well, what would it mean? Any questions? Anything? Is it a busy enough machine for you? So hybrid systems. Don't buy more zeros than you need to.
Thanks for organizing.
Yeah, I'm glad to. Yep. Yeah, yeah. Bill's already done it.
And we get points for presenting an incentive, right?
Yep.
Yeah.
Yep. And I recorded this, so I can send that recording to you if you want me to, so you can send it on to NI for proof that you presented or whatever, because I remember Petter had a huge fussing match with them.
Oh, there was one. And 1 month later, no, we need that, okay? And I added right away, 1 month later, quite. And then. Every time I send a date, like, you're good.